Okay, so we're going to do an example, Stokes Theorem for surface. It's part of the sphere, x squared plus y squared plus z squared equals 9, bounded by the planes y equals x and y equals negative x, in octants 1 and 2. Well, right here is your intersection of that sphere with the xy plane, which is where the sphere is widest. At least it's a great circle of the sphere. Here's your y equals x line, here's your y equals negative x line. If we sketch the region, well, I've sketched it over here, okay, and I was going to construct a sketch, but I'm not going to. Okay, so the region is, well, here's the line y equals x. Back here is your line y equals negative x, written a little more faintly because the region's in front of that line. We have an arc along the circle from the pole, let's say at this point, arcing down to this point here, okay, and on the line y equals x, and another one arcing down to the line y equals negative x along the sphere. And then we, add a little bit of shading and so forth. So now we have this wedge. You can imagine slicing an orange at 45 degrees this way, 45 degrees this way. Slice half an orange because we're only on the upper half of the plane. Cut the orange in half, then slice it like this. And we get this wedge. Okay. There's a little more to this wedge that I'll refer to in a minute when we get to it. You can parameterize the entire sphere by x equals 3 sine phi cosine theta, y equals 3 sine phi sine theta, z equals 3 cosine phi. And now you can check that x squared plus y squared plus z squared equals 9. Now why this parameterization? Well, that's just your polar coordinate parameterization. For the upper half sphere, the points on your sphere are represented by r vectors, if you wish, that come from the origin out to the surface and make angles from 0 up to pi over 2 with the z-axis. Well, that's your angle phi. Okay, and that's indicated down here. And this blue vector that maybe is a little faint, a little hard to see, it's kind of inside the sphere. But your angle phi is the angle from the z-axis down to that blue vector. The blue vector projects down to a vector on the line y equals x. Sorry, it doesn't. It projects onto this faint blue segment here that I'll make a little clearer. It comes along here and along here and down here. Okay, so you got this blue triangle. This is the projection of the r vector down into the xy plane, and the angle theta is the angle from the x-axis measured in the positive direction to that line. So there's your phi, there's your theta, and your r is 3 because you're on the surface of a sphere of radius 3. So that's the parameterization. Okay. Now this parameterizes the entire sphere. This segment parameterizes, well, same equations, but now with theta from pi over 4 to 3 pi over 4, because y equals x is at angle pi over 4 with the x-axis. Y equals negative x is at angle 3 pi over 4. So theta goes from pi over 4 to 3 pi over 4, sweeping out everything from here to here. Phi goes from 0 to pi over 2, giving you the upper half of the sphere. Boundaries of piecewise curve C1 plus C2 plus C3 looks like this. We'll see it in more detail shortly. R is 3 sine, well, R is your xi plus yj plus zk for this, and your x is this, your y is this, your z is this, so R is just this, and I guess your 3 cosine phi has to have a k on it. Okay, the surface area integral then is the integral of the magnitude of t phi cross t theta d phi d theta. T phi is just the phi derivative of your r vector, of your parameterization. Well, here's your r vector. And that's a straightforward derivative. Derivative with respect to phi means these sines of phi will become cosines of phi, and here they are, everything else being the same. And this cosine of phi will become negative sine of phi, so that's where you get the negative 3 sine phi times k. T theta, very similar case. Derivative is a little different. They're going to have a negative sine phi here, a plus cosine phi here, and 0 here. If you then do your t phi cross t theta cross t phi, you're going to get 9 sine phi cosine theta. This is your familiar volume increment from spherical coordinates. Okay, now that was worked out more geometrically with the spherical coordinates, but again, in terms of your t phi and t theta, you see that this parameterization gives you the same thing you would get for the rho squared sine phi cosine theta. Okay, now we continue on. And we actually started this. I actually did a full discussion of what we have here. Up. That's not it. Where'd it go? This isn't it. That's not it. That's right, I have 2 boards here. Well, that's not it either. Yeah, this is it. Well, I'm going to have to go to that in a separate video. Okay.